Okay. Welcome to the seminar series. I'm delighted today to introduce to you George Zweig. Few people have an impressive resume as him, so just to say a few things. He invented or discovered the quarks. He didn't get the Nobel Prize for it because someone else got credit for it, but he's also very interested in not just physics, but also some other aspects of engineering, and also very interested in Cochlear. Today we'll be talking about Cochlear dynamics in cochleas, looking at Hopf, bifurcation, and other things like that. And without further ado, so George.
Thank you, Gert. Well, this afternoon I'd like to talk about how you might go about characterizing the response of the cochlea, the nonlinear response of the cochlea, and tell you about a great controversy that's going on in cochlear mechanics. So, let me turn on this. Excellent, it works. So I'm going to begin by giving you a little background on the anatomy and physiology of the cochlea. Then we're going to talk about competing views of cochlear mechanics. The first and the most modern view is that the cochlear nonlinearities, the nonlinearities in the mechanical response of the cochlea, actually mirror the nonlinear response of its individual components, which presumably are the outer hair cells. And that will lead us into a discussion of the Hopf bifurcations. There's another point of view, though, that says that the nonlinear response of the cochlea does not reflect in any simple way the nonlinearities of the individual components. Their nonlinearities, through their collective action, leads to a nonlinear response which is really quite different. And that's a more complicated situation because you have to talk about the cooperation. So for that we need a model of cochlear mechanics, and what we're going to do is look at measurements of basilar membrane motion, right, and invert them to develop this model. That will lead us to discussion of a new type of bifurcation, and we'll talk about the predictions of that, and then a summary. So let me say a word about the metric, that is, in what field this talk falls. Basically, you're supposed to judge the content of the talk by how well we'll be able to represent the data. We're not going to be talking about how you might want to be inspired by this data to build, for example, a better preprocessor for a speech recognition system, although I think that there's a lot of promise there, because it's not a great exaggeration to say that most preprocessors work like dead ears, and it might be nice to replace them by systems that work a little bit like the living ear. And the essential feature of the living ear is that it's nonlinear. Okay, let me say something then about the anatomy and the physiology. So here we have a familiar representation of the ear. So sound comes into the external ear canal. It vibrates the eardrum, the tympanic membrane. That's attached at this point called the umbo, which we're going to refer to in a little while. And that umbo that is on the malleus, which is then connected by another bone to the stapes. And the stapes, as it vibrates back and forth, acts as a kind of piston which creates pressure gradients inside this structure that sets up waves. And if we were to, traveling waves, and if we were to take a cross-section of the cochlea like that and blow it up, we would see a three-chambered structure. The stapes is connected to this upper chamber. And so as it vibrates back and forth, it creates a fluctuating pressure difference between these two chambers, which then sets the central chamber into motion. That central chamber is enormously complicated, called the organ of Corti, and it contains the transducers, but it also contains effectors. It contain cells, they're called the outer hair cells, that have the ability, when they are pushed, to push back. And that's the essential nonlinear element in the cochlea. The nonlinearities arise in the nonlinear mechanical response of these so-called stereocilia, and also presumably in the nonlinear response of its ability to contract when it's stimulated. Okay, yes?
About the mechanisms, they are nonlinear.
Well, we talked about, Eric and I were talking about today, these stereocilia here presumably are also nonlinear and would be a contributing factor. The truth of the matter is that we don't know exactly where the nonlinearities are. We don't understand this micromechanics. And therefore, we're going to adopt later on a point of view which is, it's difficult for people to understand because it's phenomenological. Most people that look at cochlear mechanics say, oh, I think it works this way. And then they work out the consequences, and then it does or doesn't compare very well with experiment. Usually doesn't compare very well with experiment. And what I've done is adopt the point of view that it's too complicated to understand because we don't have enough measurements. And what constitutes success, at least at the first stage of investigation, is to be able to reproduce how the cochlea responds to any sound. That's what we want to do. We have what I would call a phenomenological description. Okay, well, there are competing views as to what constitutes success in cochlear mechanics. And one view is that you really want to write down all the hydrodynamic equations, and you want to make a model of that complicated structure, and then you want to compute its response. And any effort to simplify the problem is just not worth it. And I have here just a typical paper from a man called Colston, who says the 1D model, that is a simplified, for example, transmission line model of the structure, is unable to simulate the response of the dead cochlea, and definitely not able to reproduce the response of the living cochlea. And he says it is therefore of little value to consider further the operation of the 1D model, and he believes in these full-blown 3D hydrocode calculations. Then we have what's become really quite a controversial issue. In the last couple of years, there have been two groups, one at Rockefeller and one which is at Cambridge and some institutes in France. And they've put forward the notion that the nonlinearities that people can measure in isolated hair cells, actually not in the mammal, but in the bullfrog, that these nonlinearities manifest themselves in the mammalian cochlea, and that by measuring their characteristics in these simpler organisms, they're then able to predict what the nonlinear response in the cochlea should be. And one of these groups, who, I don't know if you know this person, Jim Hudspeth, he's probably the best experimentalist around that works with hair cells, and he was actually my first postdoc. And I think he's very, very smart. And he teamed up with some people at Rockefeller University where he works, and they're in this field called dynamical systems. And they wrote this paper in Phys Rev Letters. It's a couple years old, and it says, our hearing organ, it's not a very long abstract, our hearing organ, the cochlea, evidently poises itself at a Hopf bifurcation to maximize tuning and amplification. We show that in this condition, several effects are expected to be generic. Compression of the dynamic range, infinitely sharp tuning at zero input, and generation of combination tones. These effects are essentially nonlinear in that they become more marked the smaller the forcing. There is no audible sound soft enough not to evoke them. All the well-documented nonlinear aspects of hearing therefore appear to be consequences of the same underlying mechanism. And they have other comments, just a phrase, it seems likely that the process that poises the ear as a whole near a Hopf bifurcation is identical to that involved in bringing each hair cell to a bifurcation. And there are many papers in the Proceedings of the National Academy of Sciences that follow up on this idea or that have independently proposed the idea. And just yesterday, day before yesterday, I got a big thesis of a student that is working on Hopf bifurcations and the cochlear mechanics. So I want to talk a little bit about what Hopf bifurcations are, how you apply them to cochlear mechanics, what the predictions are, and then finally see if the predictions are correct. Okay, so I wanted to start with something simple. So we have the harmonic oscillator. We want to see what we mean by a Hopf bifurcation for a nonlinear oscillator. So let's start with just an ordinary linear oscillator where we have this familiar equation, and epsilon is a damping constant. And you know its solution is this damped sinusoid where the frequency of oscillation does depend upon this epsilon. Well, if epsilon is greater than 0, you get something that's damped and it can describe a physical process. If epsilon is less than 0, you get something that increases in amplitude, and your description of that process must therefore be incomplete. So for example, in the characterization of vacuum tubes, which can go into self-oscillation, van der Pol suggested that to describe that oscillator, one should have a nonlinear damping where if epsilon is negative, and it would look like it would go into self-oscillation, if the amplitude becomes large enough, you then increase the damping and you stabilize the system. So in this oscillator, you start off with a small amplitude, it grows larger and larger, and then it just settles down into what is called a limit cycle, just oscillating at a constant frequency with a constant amplitude. And the reason people call this a bifurcation, which means a branching, is that as epsilon goes through 0, the nature of the solution becomes entirely different. With positive epsilon, just some simple damped exponential, damped sinusoid, and when epsilon is negative, you get this limit cycle. Okay, so what I'd like to do is now define for you what is meant by a Andronov-Hopf bifurcation. So to do that, I need to reformulate these equations into some conventional or canonical form. So let me do that.
Which equations?
This equation,
Okay.
or this equation right here. So by convention, mathematicians just like to describe nonlinear or differential equations of all sorts as a series of coupled first-order equations. So they define a variable y, which is just x dot. And then this equation just becomes y dot is equal to this. So we have two coupled first-order equations instead of this one. They also like to symmetrize their equations. So they look for a transformation which is smooth, where they define two new variables, u and v. In general, those transformations can be nonlinear. But in this particular case, the transformation that they would make is they'd say, okay, we'll just make u equal to x, and v will be a linear combination of x and y where we pick the coefficients, so the resulting equations in u and v look symmetrical. And then this is what they get. Now, what they'd like to do is actually define two new variables which really capture what you're interested in, which is namely the amplitude of the oscillation and its phase. Okay, so they then define linear combinations of u, or combinations, nonlinear combinations of u and v. So they define a quantity r squared, which will be the amplitude of the system, as u squared plus v squared, and theta is just that arctangent, and that'll be the phase. And when you rewrite your equations, then what you get is just that r dot is equal to minus epsilon r. That's easy to solve. That's e to the minus epsilon t. That's just the envelope of the oscillator. And theta dot is equal to omega. That just says that this oscillator has constant frequency. And the phase, theta, is just a linear function of time. Okay, now I can tell you what an Andronov-Hopf oscillator is and when a system has an Andronov-Hopf bifurcation. It has a bifurcation of the Andronov-Hopf type if and only if there's a smooth transformation of variables so that you can find variables r and theta that satisfy an equation of this form. So this equation is just like the one up above. It just has a nonlinear term here and a nonlinear term here. And the thing that's special about it is that there are squares. That is, there's a symmetry. The equations are invariant, and r goes to minus r. Okay, so the people that try to apply this idea to cochlear mechanics say that these individual hair cells are Hopf oscillators, and they obey an equation of this form. So they set b equal to 0, and they say a is just equal to 1. There's just an r squared term here, and they say this is what characterizes the oscillator, and this is what characterizes the response of a point on the basilar membrane when it's listening to it. In this case, when it's listening to a click, because there's no driving term. Okay, now to see if their idea is right, they make a prediction. They say, okay, let me add a tone to this formalism. So I'm going to drive this oscillator, which has this nonlinearity with a pure tone of amplitude A and frequency omega 0, and let me find out what the response R is as a function of this amplitude. So when you solve that problem, what you find is that the way in which R grows as A grows depends upon what omega 0 is, how close it is to omega. And if you're driving it at very low frequencies compared to 1, basically, the square root of 1 minus epsilon squared, R grows like A, so it's a linear system. But as you change this frequency, the response of R becomes more and more compressive. And finally, when this frequency is exactly equal to omega 0, you get the most compression you can have, and R goes like A to the 1/3. And then they have just looked at the data, looked at it, and said it grows like A to the 1/3, and this is verification of their idea. Well, I want to see if that's correct. And let me just, for convenience, change the notation here and say that I want to call this exponent here alpha 1 minus another quantity. And I'm going to say it's the real part of a complex quantity nu, and you'll see why I go into that complication in a moment. So what the Andronov-Hopf people say is that the real part of this quantity nu has to be 2/3 at resonance, and at low frequencies it's got to be equal to 0. So a real part of nu is 0 when things are linear. Okay, so what do cochlear responses look like? Here's some responses from measurements that Rode made some time ago using the Mossbauer effect. And what he does is this. He measures the velocity of a point on the basilar membrane. That's the membrane on which this organ of Corti sits. And he sweeps the frequency and he sees what the response is. Then he goes to the umbo and he puts a Mossbauer source on the umbo, remember, at the eardrum. And he, once again, sweeps the frequency and sees what the response is. Then he takes the ratio. So if the system were linear, that would be the transfer function. If it's nonlinear, then they call it the describing function. So he measures this describing function. So there's an amplitude ratio, actually, as a function of frequency. And here he has a series of curves for different sound pressure level. So at high sound pressure level, 105 dB, this is what you get. But as the amplitude of the tone decreases, he gets an ever sharper describing function. And later on, I'm going to tell you that we've extrapolated this actually to the regime where things become linear, because they do become linear around the threshold of hearing. And this is what the extrapolation gives, a very sharply peaked transfer function. Okay, now what the guys say that believe in Andronov-Hopf bifurcations is that if I fix a frequency, in fact the most sensitive frequency, and I look at a fixed frequency, I look at the response as a function of amplitude, that should change as a power law, and it should be compressive. and the compression exponent should be a third. So what I did was I went back. Actually, I did this for other reasons. I was trying to find a linear limit of cochlear mechanics, but I had the data. So I went back and looked at what you get if you fix a frequency and measure and look at that amplitude ratio and plot it as a function of umbo displacement. So if the system's linear, this should be flat. It shouldn't matter what the ratio. It shouldn't matter the ratio what the umbo displacement is. And in fact, at low frequencies of 2 kilohertz or at 4 kilohertz, it seems reasonably flat. But you see, as the frequency approaches the most sensitive frequency, you get a steeper and steeper slope. So the first thing that's interesting is that there's a power law. And the second thing that's interesting, which I'll show you in a moment, is that there's also a power law for the phase, and the power laws for the amplitude and phase are related, and you can actually look at that power, that exponent, and compare it with what you get with Hopf bifurcations. So this displacement ratio D is a function of position and frequency. We fixed that, and also the umbo displacement, and that goes like the umbo displacement to some power. And the real part of that tells you how the amplitude changes, and the imaginary part tells you how the phase changes. So you can plot then the real and imaginary parts of the umbo displacement as a function of frequency, and this is what you get. So if the system is linear, the real part should be 0, and so a linear system would be down here. But in fact, this is what you get. It's highly nonlinear. The Andronov-Hopf people say that at the peak, this should be 2/3, which is about here. And it isn't. It really isn't. And they can't get any number, any compression, which is greater than 2/3. So that hypothesis just doesn't work. It's just wrong. Now, there's an interesting thing that I noticed, which is that the real and imaginary parts of nu, which are really related to the compression slope of the amplitude and the phase, they're actually Hilbert transforms of each other. And I don't quite know what that means, except that it's a strong constraint on any, that is, I don't know what it means physically, except that it's a strong constraint on any theory that you're constructing for nonlinear cochlear mechanics. So what I mean by a Hilbert transform is that the real and imaginary parts obey these two relations. All right, so we find that Andronov-Hopf bifurcations don't work. So we have R at the peak goes like not 1/8 of the 1/3, but 1/about 8 of the 7.5. And other people have, using other methods, found that R grows like 8 of the 1/7. Now there's another interesting prediction that you can make if the system is just a two-dimensional system. It's really just completely described by the Andronov-Hopf oscillator. You can compute the impulse response, right? We had that equation. You can find its solutions. So here's the solution. So here's R, the envelope of the impulse response as a function of time. When time is 0, then what you find is this cancels this, and R of t is just R of 0. And for long times, you can drop this, and the amplitude just goes like e to the minus epsilon t, just like it does for an ordinary harmonic oscillator. But it's monotonic. Monotonic. Okay, now, what do real impulse responses look like on the basilar membrane? So there are measurements made by Ruggiero and other people. And I have here for you the impulse response. This is in the chinchilla. And let me show you what's plotted. Time goes this way. Displacement of a point on the basilar membrane is plotted over here. And you see, and the sound pressure level of the click is plotted here. So if the click is very quiet, 14 dB, you hardly see anything. At 24 dB, you see this structure. At 34 dB, you get the structure that's clear. Pardon me?
How do they measure these?
This is measured with laser interferometry.
Okay, on a live?
On a live, yes, absolutely. If the animal isn't live and in great shape, you don't see any nonlinearities.
click is at 0 or?
The click is at 0, yes. The click is right, the click is, well, yeah, the click is at 0, right here. Now, the thing that's very interesting is that you see eventually at high levels 2 responses. The thing rings, and the amazing thing is, it's hard to see from where you are, is that there's a phase reversal of 180 degrees. So these things are really beautifully in step at a particular frequency. And then if you were to extrapolate this out here, you'd find that the peaks would be exactly in the valleys. So it's a very characteristic response. The other thing which is very interesting is that the zero crossings are invariant. They don't depend upon sound pressure level, at least in the first peak. Here you do because you get a phase reversal. So that's an interesting characteristic. So certainly it's not monotonic. The other thing that's interesting is that at higher sound pressure levels, the impulse response becomes much more compacted. Its envelope becomes much more compacted. So really what happens is that at low sound pressure levels, you have a longer time window for analysis so that you can do a better job picking signal out of noise. At higher sound pressure levels, you care more about timing resolution because you don't need that other ability to pick signal out of noise, and this becomes more compact. Why there should be this kind of structure is not known. But it's very characteristic, and again, if you think you have a theory of cochlear mechanics, you should be able to get that. And it's hard to get that. The vertical line here was placed so that people could see that the zero crossings are independent of the sound pressure level. All right.
So that will imply that there's very little phase distortion.
Pardon me?
That will imply that there's very little phase.
Very little phases. So, for example, if you were trying to build a filter bank, where you're going to analyze speech and you have 2 of them for the 2 ears, and you want to make those filters nonlinear, you would like those filters to have the characteristic that the zero crossings would be independent of sound pressure level, because when you compare the output of the 2 ears to localize, it'll make your job much easier. All right.
Or conversely, if I would use a localization algorithm, it says that the zero cross is as good as anything else.
That's right. That's right. Okay, so now, given that the Andronov-Hopf bifurcation doesn't work, and if you wish a zero-dimensional cochlea isn't really what you want, or at least a zero-dimensional cochlea that has a Hopf bifurcation, let's talk about how one might go about getting a model of cochlear mechanics that at least gives you a description of what goes on, if not an understanding of what the micromechanics of the cochlea are like. All right. Well, we have as measurements the subscribing function. Now, these measurements are made at a single point, and what you'd really like to know is how things move over a spatial interval. And there's a way of doing that if you notice that there's an approximate symmetry in the problem. Let me explain that to you. Here we have a picture, a diagram of the cochlea unrolled, and a snapshot, instantaneous picture of what the displacement of the basilar membrane might be like in response to pure tone. Now it has an envelope, and within that envelope you have a traveling wave, and the wave has the property that the wavelengths get shorter and shorter until you reach some point at which the displacement really drops to 0 when the wavelength goes to 0, it gets very small. Now the symmetry is the following, that if I change the tone's frequency, all that happens is that I translate the envelope to a different position. So if I increase the frequency, I go this way, and I decrease the frequency, I go this way. And the points on the basilar membrane just go up and down at the new frequency, but the envelope just translates. Now this isn't right in a global sense. In other words, if I play a very low tone and I go down here, this envelope looks quite different than this one. But all you need in the analysis is that the symmetry holds over the region where the peak is large. That's all you care about. And there is evidence, experimental evidence, again by Bill Rohde and now by others, that this local scaling symmetry holds. If that's true, then this describing function, which should depend upon both position and frequency, depends only on a single variable. And that variable we call beta, and it's the frequency divided by the resonant frequency of a particular point at which you might be at. Yes, Andreas?
So this model, is it fair to say that this model is a phenomenological model for the cutoff regime of wave propagation, not for the local wave?
It's fair to say that this is the model I'm going to present you, I believe, is right in squirrel monkey above about 2.5 kilohertz. This is a prejudice that I have, and that is that I think that the hearing or the cochlea in mammals really has two very different regions. One is low frequency, which we've inherited with some modification from the lower vertebrates, who only hear at low frequencies. And then we have grafted onto it something which evolved that allows us to hear in the higher frequency region. And I think that what I'm saying is applicable to this other part of the cochlea, the newer part of the cochlea that is responsible for the higher frequency regions of hearing. Okay? Yes?
Now, you're stimulating with the sine wave.
Pure tone, yes.
Pure tone.
Pure tone.
But it's nonlinear response. So does that mean that it's not sinusoidal at each point on the vascular membrane? Or is the nonlinearity a grosser effect on the amplitude?
Okay. That's a good question. Empirically, when you play with a pure tone, or simulate with a pure tone, there's very little overtone that you see in the response. It's overwhelmingly just at that frequency, and not at the overtones, or not at the subharmonics. That's just an empirical fact. That's the first point. The second point is that what I'm going to be doing here is trying to understand the problem by first going to the linear regime, which really does hold at low amplitudes. You can show that, like at 10 dB, using another set of techniques, otoacoustic emissions, that the cochlear response in humans at 5 dB, for example, or 10 dB is really a linear response. So what I really want to do is take these nonlinear responses, extrapolate them to low sound pressure level, determine a transfer function, try to understand that transfer function and what it implies about the nature of the underlying oscillator. And then I want to make that underlying oscillator nonlinear and then use that to predict the nonlinear responses of the cochlea. So for what I'm doing now, we don't have to worry about the issue that you raised, because what we're going to do is we're going to just work with small umbo displacements where this thing doesn't depend upon the umbo displacement anymore, and certainly there are no overtones. But it also happens to be true that as you go to higher sound pressure levels, the overtones and also the combination tones, if you play two tones, are very small. They're there, but they're small. Which is actually a wonderful problem that is really being addressed here, or will be, and that is, how can you get a system which is enormously nonlinear? I mean, it's nonlinear almost from the threshold of hearing to 120 dB, and have such small harmonic distortion. I mean, it's a hi-fi cochlea, really. There are combination tones, but they're not horrible. And that's one of the underlying issues that has to be resolved, and we're going to talk a little bit about that. Okay, so we know that we have a wave-like response when we listen to a tone. And we know that there's a wavelength, and if that wavelength were constant, we could say, oh, look, this describing function would actually just look like a traveling wave, just something like this. But we know that the wavelength varies, and it varies slowly. It doesn't change much within a wavelength. And so it has a representation where you change beta over this wavelength to this integral of beta over the wavelength. And then there's something out here in front which depends upon details of the model. So the idea now is the following. To take the measurements of this displacement ratio, extrapolated to low sound pressure level, solve for the wavelength, and then relate the wavelength to the oscillator. So we're going to try to discover the oscillator that way.
At each point.
Pardon me?
At each point.
As a function of beta. We don't have to worry about beta and frequency are sort of connected because there's only one variable, so you're going to do that at each beta. Now, practically what that means is, yeah, you pick a particular point at which you do the processing, and then you find the answer, and then you replace your frequency variable by this variable, and then you know what it is at other points. Okay? That's the idea. Okay, so we want to find the wavelength squared. So you do that, and you get some set of numbers. It's a numerical procedure. The remarkable thing is that the set of numbers you get is very closely fit, this wavelength squared, by this thing that you see here. By the way, S is I beta. It's like the double ES. So at resonance, S squared is equal to -1. So you see, this is what you get for the wavelength squared. It looks like a harmonic oscillator. That's what you'd have for a harmonic oscillator. But it has an extra exponential term. Now, what this means, and now you have a theory that relates the wavelength squared to the oscillator, and that theory I'm not going to go through in any detail. Let me just say that the wavelength squared is just proportional to the Fourier transform of this thing. So that this wavelength squared says that the underlying oscillator looks like a harmonic oscillator, but it has a time delay force. And if you put that on the other side, you can think of that as a feedback force. You can think of it as a harmonic oscillator that has a time delay feedback force, and it turns out epsilon to fit the data is negative. So you have an unstable oscillator which is stabilized by a time delay feedback force. So let me tell you, or show you whether or not this works. Should you believe any of this?
Josh, a quick question.
Yes.
So to get there, you use this expression that you had in the previous slide.
Yeah.
Did you dream those expressions? How did you get those? You just put them out. You just dream those.
Okay. Technically, if you apply the WKB approximation to a nonlinear, to a linear transmission line, this is what you get. Now, the geometry, affects this coefficient, but doesn't really affect this term. This is what a wave looks like with a wavelength. What the details of the model relate to is how you go from the wavelength squared to the oscillator. And I'm just giving you the results in a model where the wavelength of this traveling wave is long compared to the height of the chamber. And I'm not worried about, that's just a phenomenological, that's an approximation that you make. And the oscillator that you get has in it all the details of the oscillator is in the organ of Corti, as well as any approximations that you might have made about the geometry. So the oscillator I'm talking about is not the outer hair cell oscillator, but it's an effective oscillator. In other words, this system that has these long wavelengths has a cochlear response which is nearly identical to the real cochlea, but there isn't a simple one-to-one correspondence between the two. I'm just setting as the goal a phenomenological description where I can reproduce the response of the system, okay? The thing that's a miracle is that the response is so simple. Let me show you the fit. So we have an amplitude and a phase for this describing function. These are the extrapolated amplitudes and phases. The dashed lines here are Hilbert transforms of each other. So you can see that the extrapolations which were done independently didn't give you crazy answers. The dotted line is what you get if you assume that the wavelength squared has the form that I just showed you, which I can't find, has the form which I just showed you. Yeah. If you say the wavelength or the oscillator is this, And if you say that epsilon is minus 0.06 and rho is small, 0.14, and tau is 1 3/4 cycles, if you say it's that, then you get the dotted line. Now actually the best fit with those parameters looks much better, but I thought it was misleading to show you the best fit because it doesn't really reflect my attitude towards the fit. So I'm giving you a fit which is a good fit but not the best fit. But you see that over a range from about, 10 dB until 80 dB, it gives you an incredible fit to the data. So this is actually an interesting thing in the following sense. The fact that these are Hilbert transforms of each other means that they're not independent. So how many numbers do we have? We have like 11 or 10 numbers, which are just these numbers. So those 10 numbers have given us that functional form. And now with 3 parameters, we can characterize this. But, and now we're coming to the bifurcation, if you ask where the zeros or the poles of the transfer function are, the zeros of the wavelength squared, since there's this complex exponential, we get an infinite number of zeros. So I'm giving you the zeros of s squared plus 2 epsilon s plus 1 plus rho e to the psi s, 2 pi mu s. And this is what you get. You see, you get 2 zeros, which are very close to each other, and there would really give you the peak. And then you get these others. Now, the fact that these are close together isn't interesting. In other words, if I made them just 1, I'd get a fit which was just as good. So, in fact, all we have is a 1 parameter fit, that is the distance of this double pole, and put them on top of each other, from this axis. So you got 1 parameter which fits about 10 points, and these 10 points are distributed over about 80 dB. And that's the miracle. That's the miracle. Okay, so now let's go and talk about what's meant by bifurcation in this case. In the old case, the harmonic oscillator case, rho was 0. We got rid of this term right over here. And when epsilon went through 0, that was at the edge of stability. Now you can say, okay, that double pole, suppose it were right on the axis. Then I can determine all my parameters. And if I do that, I get the parameters that you see here. So they're pretty close to each other. So this thing really tries to be close to this bifurcation point. But the bifurcation is not an Andronov-Hopf bifurcation. It doesn't have a name. It's a bifurcation that you get from time delay systems. And the interesting thing is that the way you use the bifurcation is not by trying to directly predict the response of what's going on when you listen to tones, but you use it to determine parameter values.
George,
Yes?
how can you get a bifurcation on either system? There's a linear.
Okay, I'm going to show you that in a moment. So let's do that right now. Let's make the oscillator nonlinear. So here's the oscillator. What Van der Pol might have done is just put in an x squared term in the damping. I'm not going to do that because that generates a lot of combination tones. So I'm going to say what I want is that the damping depends upon the envelope. I set the operating point of the system, and that really deals with the energy in the oscillator. This is the energy in the oscillator. This is the kinetic energy. That's the potential energy. So I'm going to say that. I'm going to get a hi-fi oscillator. I'm going to say, what does that response of that oscillator look like to an impulse? And here it is for different strengths, different derivatives at the origin. So for quiet impulses, you get something which rises and then dies down. Then as you increase the level, you get this pinch, and you get a 180-degree phase reversal. And as you increase the tone further, you keep this pinch, but everything shifts. So qualitatively, it gives you what you actually see. And it's just a single isolated oscillator. And it's that oscillator that has this kind of bifurcation that I was just discussing.
That's an instantaneous energy.
It
would have to be from an impulse response.
Well, yeah.
You're hitting this with the click.
Right, and what it is the energy in the oscillator. In other words, you've got this oscillator and it's the sum of the potential plus the kinetic energy. This isn't quite the envelope. If you look, this isn't exactly the envelope, but it's close to the envelope. So in other words, the energy in the oscillator doesn't change much on a cycle by cycle basis. I mean, this thing has got it.
That's R
Is
squared,
that,
right?
pardon me? It's essentially, yeah, thank you. It's basically R squared. In the old notation, it's R squared. Yes.
So now, again, your model, you decouple everything. I mean, you decouple N nodes on the Cochlear, and you represent each node with a phenomenological oscillator. But the oscillators are not coupled together.
Now they're not coupled. So the next thing that I've got to do is I've got to couple these oscillators together, because I don't believe that you want to describe it as an isolated oscillator. What I want to say is that I haven't found a reasonable way of generating these kinds of responses other than through some kind of non-locality like this time delay. Let me just go back and try to interpret a little bit what we've seen. What we want to do is couple these oscillators together. Let me, for the moment, provide you with an interpretation without the nonlinearity, and then we'll put the nonlinearity back. The oscillators that we have are coupled through the fluids, so that when a point on the membrane goes up, it acts on the fluids, which get displaced, and they act on the neighboring points. So we have this 1D fluid coupling, which is passive. Now, we have a negative damping. That is, we have a force that acts on a very rapid time scale that cancels the damping that has to be there because of all the viscous forces. So what happens is, as the membrane, for example, is going up, something's pulling it up even more. Presumably that's the outer hair cells, but we don't know. The interesting thing is that the damping you have is so large that it makes the oscillator unstable. You might say, well, just go and cancel the damping that's there and put it close to zero and forget about it. But actually, there's so much damping that it makes it unstable, and you have to put in a long-range stabilizing force. That's that time delay force with 1 3/4 cycles. Now, why do you do that? Well, I don't know why you do it, but the result of doing it is that you end up with an oscillator that has the property that if you look at its impedance, you know that an ordinary harmonic oscillator, it's either the real or imaginary part of the impedance vanishes. I guess it's the imaginary part that vanishes, and the real part is just the damping. Well, with these parameters and with this over-cancellation, what happens is that in this oscillator also the real part vanishes. Not only that, if you take the spatial derivative of the impedance with respect to frequency, both its real and imaginary parts vanish. And if you ask yourself what kind of oscillator gives you that property that the real and imaginary parts of the impedance vanish and the real and imaginary parts of the derivative of the impedance vanish, then you have to have an oscillator with negative damping and a long time delay force. That's the only way you can get it. So it is a very special, interesting kind of oscillator. Now this oscillator has this time delay force, and it's just important to note that a time delay feedback force on an isolated oscillator can be made similar to an instantaneous feedback force that gets its feedback from other points in the Cochlear. In other words, if you're an oscillator and you're going back and forth and you're trying to figure out what feedback force you should act on you look backward in time and you saw where your oscillation was. But if you're an oscillator in the Cochlear and you're going back and forth, points around you are also going back and forth, and you can get the displacement that you need or the number that you need to figure out the force you should have by looking at neighboring points.
This is presumably using the tectorial method.
I have no idea. Could be.
Otherwise, you couldn't control the phase at which you want your input.
That's right. You have to control the phase.
System to couple to.
Well, for example, there's an electrical system.
I see.
You have the cochlear microphonics. And so that's another possibility. I have no idea. Yes? Eric?
How large was that? How large was the?
1 3/4 period.
1 3/4 period.
1 3/4 period.
So that's quite a ways from this, isn't it?
Yeah, but it doesn't, yeah, it's quite a ways.
So it's not the adjacent.
No, I think the adjacent stuff is what's giving you this negative damping. The hair cells right around where you are giving you this feedback force that's canceling your damping. Okay, and you get this phase reversal and an isolated oscillator, and it comes from that non-locality. If you have an isolated oscillator, I just can't get a pinch any other way with a phase reversal. So I think there's something here. I don't exactly know what it is in terms of the fundamental micromechanics of the organ of Corti, but the fact that we got this oscillator and then you just put something in and you get this strange phenomena out means that you've probably got something right. And I think what we got right is, I'm absolutely positive that we know how the squirrel monkey cochlea responds to any sound at low sound pressure level where the frequencies in the sound are above a couple of kilohertz. Okay, that's what I know we can predict. I'm absolutely sure that that's right. Now, later on we'll talk about what we can do with a nonlinear response. But let me just summarize by saying that, you know, the Andronov-Hopf bifurcation, some fad, it's an enormous fad. Thank you. I'm going to take about 5. They're just not relevant for mammalian hearing. But there is another type of bifurcation that is, and thinking about bifurcations is interesting because it allows you to determine parameters. Bifurcation theory is really relevant for systems after long times. If you've got a complicated system that's got lots of oscillations, you're not going to describe it with this simple bifurcation second order system. But if you wait long enough, everything settles down except the longest lasting mode, and that's the mode that's being described here. So in general, using bifurcation theory in hearing is a terrible idea because hearing cares about describing the response to sounds that are highly transient, highly non-stationary. And bifurcation theory really doesn't do a reasonable job with that. But on the other hand, thinking about bifurcations, that is, thinking about somehow being close to instability, is a good thing to do if you're trying to understand the response of the system, but in the way that we've done. Okay, we've got this phase shifting pinch that occurs in the impulse response in an isolated oscillator, which has this time delay, and I haven't yet told you what happens when you couple all these together because I'm in the middle of that. That's what I'm working on now. I want to sort of finish, at least this part, by characterizing the model that we've just talked about in terms of an equation. I mean, when you've got a wave, you have a wave equation. And the wave equation that describes the model that I've been presenting is this one. D is the displacement of the oscillator. This is a wave equation if this is a distance and this is a wavelength. Now, this is a distance, this coordinate tau is a distance in the sense that it's the period, the natural period at the point z. So in that way it represents a distance. So we're going to use that as a variable that has the dimensions of time, which is the same as this. And this would be just like a wave equation where this is a distance if this were a constant. But in the cochlea, this thing is actually an operator. And it's an operator in the following way. If we define an operator s hat, which is a time derivative multiplied by this tau, so it's a dimensionless operator, then if we go to the wavelength squared that we had before, this s squared plus 2 epsilon s plus 1 plus this exponential, and everywhere we had s, we put s hat. And then we stick that down here, that's our wave equation. And that's a kind of a generalized wave equation. I've never seen it anywhere, but that's the one that describes the system, and it certainly describes it correct near threshold And I think what happens is that when you make this nonlinear in the way I just indicated, then you have a description for the nonlinear for the nonlinear cochlea, and you can work out its responses, which is what I'm doing. Oh, now Colston, you know, he and other people that think you should do a full-blown hydrodynamic calculation to characterize the cochlea, I think that they'll be right eventually when we actually know enough what the cochlea is like, so that we can characterize the organ of Corti in a proper way. But until we do so, there's not really much sense in making the model more complicated than you need to explain the data. In other words, I could go back, in fact I did, I've done two-dimensional models and three-dimensional models. You get nothing extra. So why introduce all of that complication? On the other hand, if you want to describe all the nonlinearities in the cochlear response, it may not be possible to do it with a simple one-dimensional model. I'm just not sure yet. We have to try to see. Okay, let me finish with a couple of comments about the role of mathematics and biology and cochlear mechanics in particular. Einstein has this quote that says, everything should be as simple as possible, but not too simple. So I think the Hopf bifurcation stuff is just too simple. And right now, these 3D hydro code calculations of the cochlear response are just too complicated. You just don't need it. Stan Ulam, who is an interesting guy, he was a Polish mathematician, if you haven't heard of him, and he, among other things, was crucial in the invention of the hydrogen bomb, was very interested in biology. And after Kennedy was elected president of the United States, he said, ask not what mathematics can do for biology, but what biology can do for mathematics. In general, I think he's right, but I hope I've convinced you that at least there's some role for quantification in cochlear mechanics. Thank you.
So, George, I'm trying to remember the way that that's what we got into this bifurcation.
Yes.
It seems to me that I've heard him give a talk. I didn't really follow him entirely, but they really are relating into the nonlinearity in the cilia.
That's right.
And not to the nonlinearity.
That's right. That's right. I mean,
so
you know.
It could be that this would work for the frog sackers.
Yeah, I don't have a comment or an opinion about that. That's right. That's right. I think it's perfectly reasonable for that system, but I think he feels compelled to, well, maybe I shouldn't talk about Jim and his personality, but I think they're trying to make it relevant to human hearing. Now, I can say something which is a little more sophisticated. They didn't say this, but you could say this. You could try to help them. So we're going to try to help them. I'm going to say, look, it's not fair to sit at a fixed point and vary the amplitude of the input and see what your response is, because the peak of the traveling wave shifts. And so what you really want to do is you want to follow the peak of the traveling wave as the amplitude increases and see how that amplitude of the peak of the traveling wave changes as a function of input amplitude, and see if that grows like 1/3. If you do that, you're going to get a number which is better than the number that you get if you sit at a fixed point. The trouble with that is that it ignores the fact that in order to get the response at the peak, what happens is that you have a wave which is propagating through a region where it's getting amplified. And Hopf bifurcations don't describe that region of growth. In other words, that only works near the resonant point. They can't say what happens far off of resonance. They don't believe that they can say anything about that. So what determines the height of the peak of the traveling wave in the cochlea is not just the absolutely local responses of those oscillators, it's also the oscillators away from that peak, which are not described by that theory, and therefore they're not going to be able to capture correctly what the growth is even at the peak of the traveling wave. The other problem with Hopf bifurcations, or any kind of bifurcation theory, if you try to use it the way that it's being used, is that it only really holds asymptotically in time. And you just, for example, I showed you what the impulse response is for the Hopf oscillator, and that's true if the system has only 2 degrees of freedom. If the system has like 20 degrees of freedom, which it presumably has, then you have many modes of oscillation. And the only thing that the Hopf bifurcation theory will tell you is sort of what happens asymptotically in time when after every other mode has died out. But who cares? Because the interesting region in an impulse response is what happens in the beginning. So the impulse contains lots of frequencies. And the Hopf bifurcation theory is only good for the frequencies right near resonance. So just like they can't describe what happens to a traveling wave on the basilar membrane because its amplitude is really affected by what happens at points away from that point, so too can they not represent what happens in an impulse response because there are many frequencies and they can only deal with a small number of frequencies in that impulse, which are around the resonant frequency of the oscillator that they have. So I just think that the whole idea is a terrible idea. It's just not going to be helpful.
So where does the sharp tuning that's been observed come from? Is it because as the tones progress down the basilar membrane that they're being amplified?
Yeah, that's right.
My understanding
What makes it so tall?
But there's a very sharp
cutoff
to the high frequency end, which is
that's correct.
Closer to the states of the.
That's right. I think I showed you a picture of. Well, basically, this is if you adopt scaling, then this response at a fixed point as a function of frequency is the envelope of the response as a function of position at fixed frequency. So you've got this tremendous asymmetry, this great fall off. And what actually happens I didn't show this to you, but what you can do is you can say, all right, as the wave propagates, how much energy does it have? And what does the energy flow look like that passes through a plane in this cochlea? And what happens is that as it propagates, well, I'll tell you what the answer is. Oh, I can't exactly show it to you. The answer is that as the wave propagates, energy gets pumped into it. And it's pumped in all the way, this is the stapes now, so all the way up here, the energy, more and more energy is getting pumped into it until it reaches some point which is very close to this point here, close to the peak, where the process reverses and all the energy actually gets dumped into the cochlea.
But you need another structure to store the energy and distribute it later where you want it.
Well, it's the fluid. It's in the motion of the fluid. In other words, you have energy in the oscillator and energy in the fluid, and you can ask how much energy passes past this point. And when you look at that, the energy flow, that's what happens to the energy.
And what sucks it out?
What? The oscillators suck it out. It's in this time delay system.
So the fluid cannot selectively pass the energy back to something else.
Well, the fluid has kinetic energy. It does. I mean, it's moving. There it is, and it's got kinetic. It's got mass, and it's got a velocity, and so it has energy. It has an energy density, and these oscillators are going up and down, and as the fluid goes, there's more and more energy in the motion of that fluid, which also then translates into more and more energy in the oscillators. I mean, you can actually compute it explicitly. And that's what you find when you compute the energy flow in the cochlea, that it builds up and then it dies down.
So where is it being distributed?
Yeah,
Where is it being dissipated?
yeah. That was my question too. It must be shuttled to some other systems.
Well, no.
It's not cheap, we know that.
It's being dissipated because it's doing work. There's this time delay force.
You focus more than oscillator.
It's,
There's a wave back.
pardon me? Yeah, but the question is, they want to know what's getting hot. Is that right?
I see what you're saying. It's a bit more than this way that gets bad, you know, but I think it's
And I don't have to think about what's getting hot.
we know that the cochlear doesn't generate much heat. I mean, it's very...
No, but there's energy in the traveling wave, and what I'm telling you is absolutely true, that the amount of energy that passes any plane in the cochlea increases until you reach some point where it decreases. Now, the system is completely characterized by these oscillators, so somehow in the oscillators the energy is getting dissipated, and I don't quite understand
Or
how.
moved around.
Pardon me?
Moved around. I mean, it may not be dissipated. I mean, it may be shuttled around. Right?
It's a well-designed system that should be in the inner ear somewhere.
Yeah,
So that's where you want to get.
that's right, but I don't know what the
You
answer
have
is.
to work that one.
That's right, I should do that, and we'll do that. Other questions or comments?
You're not modeling any wave back properties of the program.
Well, for engineers, there's a nice way of representing it. You basically just have a one-dimensional transmission line. So what the system looks like, the system looks like an inductor, which represents the inertia of the fluids as they go back and forth this way. And then you have another inductor representing the inertia of this degree of freedom. And then you have some spring constant. And then you've got some damping. I guess they draw this way or something. I forgot how you do that.
Resistor.
Oh, resistor. Yeah. I know how to do a resistor. Okay, so this is the dead cochlea, and what happens in the live cochlea is that you have another box here, which has, just like this had circuit property R, this is this rho e to the minus, well, it's 2 pi mu, where mu is 1 3/4 times s, so that would be I omega. So that's what you have. And the model that I just described has this negative, and actually what you have is another term, which is a very fast time delay term, and it cancels this. So the model that you have is where you have a negative resistance, and then you have this which stabilizes it. And there's only very special values of mu here which will give rise to a stabilization. And so now what you do is you say, all right, then I have another term which is the energy that's in this part of the system. It's basically the inertial. This is the x dot squared term, and this is the x squared term. And so there's this. I don't know how to write it, but there's this x squared plus x dot squared term, which is the energy in this system. And now when you ask me what happens to the energy, I don't exactly see where it's getting. I mean, in this model, I know what passes by each cross section, but I don't actually know where it goes.
Well, it's there in the minus R symbol. Minus R is not a physical device. It must have.
Right.
It has a generator in it, so that's who actually stores it.
Yeah, I mean, this minus R is a plus R, And then there's another term here, which is a fast, presumably a fast time delay force with some other. And then if you power series expand this, then you'll cancel this in the first order term, and you're allowed to do that because mu prime is very small. And so what happens is that it's supposed to get lost in here, and so what's getting hot is the fluids, except like what Eric says, no, it's going to be somehow the energy that it takes to open the channels in the stereocilia of the inner hair cells. But I don't know what happens. There's an interesting question. Well, I mean, what happens is that, I mean, this is the way you should think about it. This model then tells you how the membrane is moving up and down. And now you have to go in with a micromechanical model, and that micromechanical model will tell you if it's moving up and down this way, the tectorial membrane and the reticular membrane are moving this way, and I'm really losing my energy in stimulating the stereocilia of the inner hair cells. I mean, that's what you would actually have to do to try to figure out how much of the energy goes to the stereocilia of the hair cells and how much goes to the fluid. You have to have a model of that micromechanics, which we don't have yet.